David Bressoud, president of the Mathematical Association of America, among many other things, who gives the experimental math seminar today, developments in alternating science matrices. Amy Cohen asked me also to remind you that they will give tomorrow the colloquium talk on a slightly different topic, but equally almost as interesting as education. And also Amy asked me to invite you to lunch in honor of David tomorrow at 1:15 p.m. at the faculty dining hall. Today we're going to take Dave out at 6:45 to the restaurant Spices Inn. And it's at 371 George Street. If you'd like to join us, you're most welcome, but please let me know immediately after we talk.
Thank you, Doron. And it's
and sorry. And this book is a masterpiece. I recommend it. Proofs and Confirmation is an award-winning masterpiece by David Bressoud. Very, very strongly recommended. It's a really, one of my favorite.
Are you going to have a stall selling your books tomorrow like a concert?
Absolutely. Well, there is a sense of carrying coals to Newcastle near us, since Doron is one of the experts in alternating sign matrices, and in fact, he's going to figure prominently in this story. But I figure not everybody knows all that he and I know about these, and I really appreciate this opportunity to have a chance to talk about two things that I care about tomorrow, the transition from high school to college mathematics. And today, one of the most beautiful stories in mathematics that certainly I have ever run across. And it's a story that I wrote about in the book that appeared in 1999. It's been 11 years since then, and a lot has happened. So my intention today is to do a brief overview of the major events that led up to the ultimate proof of the refined alternating sign matrix conjecture that took place in the mid-90s, but then also talk about some of the other topics, some of the places that this field has gone since then. So I'll look at, very briefly, counting symmetry classes of alternating sign matrices, fully packed loop configurations, Ilse Fischer's recent proof of the refined alternating sign matrix conjecture. And then this is a seminar on experimental mathematics. I hope to show you that it's easy to do experimental mathematics with alternating sign matrices. And as an example, I'm going to finish up by looking at what an undergraduate at Carleton College, not at Macalester, but Carleton's a pretty good place, just down the road from us. And just some idle exploration that he was doing, and came up with some interesting results. So I'll start out alternating sign matrices, combinatorial object that was first studied by David Robbins. In 1980, this is really in connection with some work that he was doing on the Dodgson determinant, but he came up with these objects that he started to try to count. So they're square matrices of zeros, ones, and minus ones. Each row has to sum to +1, each column has to sum to -1, and the non-zero entries in any row and column must alternate in sign. This is a representation of a 5x5 alternating sign matrix. It's Greg Kuperberg's representation. I like it so much I put it on the cover of my book. So you can think of alternating sign matrices as simply square jigsaw puzzles with two shapes for the pieces. You've got this shape where the in tabs are opposite each other, and that shape can either be placed vertically or horizontally. And then you've got this shape, the blue shape, where the in tabs are on adjacent sides, and of course there are 4 orientations on those. And what you want is out tabs along the bottom and along the top, and in tabs along the left and the right. And basically what you're asking, if you want to fill a jigsaw puzzle, 5 by 5 jigsaw puzzle with these pieces, how many ways can you do it? And so what you've got to have is the first green piece you hit in any row or column has got to be placed vertically, and the next one is placed horizontally, and the next one has to be placed vertically. And once you put the green pieces in place, all of the other pieces are uniquely determined. So how many are there? And Dave Robbins fairly quickly came up with a nice simple way of counting these. What you can do is to take your alternating sign matrix and translate it into what he called a monotone triangle. So you simply take that first row, and there's going to be a single 1 somewhere in that first row. You record its position. You then add up the first 2 rows. When you add the first 2 rows, you're going to wind up with 2 1s in that sum, and you record the position of those 1s. So the -1 below the +1 puts a 0 in the second position, but we've now picked up a 1 in positions 1 and 4. And you continue this, so you add the first 3 rows and you record the positions of the 1s there. And what you get is a triangular arrangement where you have strict increase across each of the rows. The bottom row is going to have to be 1 through 5 in this case. And you've got weak increase as you go up along any of the diagonals heading toward the northeast. You've also got weak increase as you come down the diagonal toward the southeast. So you can simply describe this counting problem as the problem of counting monotone triangles. Well, you can build up the number of such monotone triangles recursively, and I'm going to do it actually the way Ilse Fischer does it, which is to begin by looking at all of the monotone triangles with a bottom row of length 2. And if we're working with the 5 symbols 1 through 5, you've got 5 choose 2 ways of filling in that bottom row. And for each possible way of filling in that bottom row, you can ask how many monotone triangles, bottom row of length 2, with that particular bottom row are there. So if you've got a 2, 4, above it you could have a 2, 3, or 4. So there are 3 ways of constructing a monotone triangle with 2, 4 as its bottom row. And now you can recursively build that up. So if you want to know the number of monotone triangles that have 1, 4, 5 as its bottom row, well, above a 1, 4, 5, you could have a 1, 4, or a 1, 5, or a 2, 4. You can't have a 2, 3 above a 1, 4, 5, because you can't have this 3 sitting above the 4, 5 combination. So what you can do is just take a look at all of the rows of length 2 that could sit above this row, and add up the number of monotone triangles for those. And then you simply repeat this process. So you look at all the possible bottom rows of length 4, and by looking at what rows can sit above those, you can count the number of monotone triangles with this bottom row, and eventually the number of monotone triangles with that bottom row. And even with the limitations of computers back in 1980 when he did this, Dave Robbins was able to calculate these for the numbers of alternating sign matrices up to 20 by 20. So he had a lot of data to work with on that. And he began to look for some pattern, some way of some nice formula for the number of alternating sign matrices of size n. And as he generated these numbers, he discovered that their factorizations involved primes that were ridiculously small. There had to be some nice formula in terms of factorials for them. As he began to look at them, he realized that rather than looking at the total number of alternating sign matrices, it made a lot more sense to work with this row. Because if we take our 5 by 5 alternating sign matrices and represent that number by a row of 5 numbers, then for the 6 by 6 alternating sign matrices, we'll get 6 numbers to work with, and 7 by 7 we'll get 7 numbers to work with. We'll wind up with a nice triangular arrangement of numbers, and there's a better chance of finding some nice patterns if you're working with a triangular arrangement rather than a